Okay, so let's explain the difference between a delta and a Y. And specifically what I want to talk about is how it applies to the load. So here in this diagram, I have three different examples, and each one is going to have a delta and a Y load. So on this right here, even though these are 50 millihertz, I just did that so that way we could slow it down so you can see it. Each one of these sources is an AC source with a voltage amplitude of 100 volts. And it's just a three-phase source. So it's phase A, phase B, and phase C. And I have three switches here that I can tell it to turn on the upper load, which is a delta, or right now the lower load, which is a Y. And so we can actually just look at currents through each of these, and then we could click on the source, and we can look at the load that's going out. Okay, so what I want to talk about first is this delta. So in this example, this setup right here, all of our resistances are the same. So what I mean by that is that the resistance of these coils on the delta are the same resistance of the coils on the Y. And what you end up having is you end up having higher currents on the delta, 3 times the amount, and it's actually a fairly simple reason, is because the voltage applied to these coils on a delta is a phase-to-phase voltage. Therefore, the voltage is the square root of 3 times higher than you would expect, and these lines right here show our phase currents, and these are the currents inside the coil. Over here on the left, you can see currents. These are our line currents, and you can see that our line currents are the square root of 3 times higher than the phase currents. And it's going to be a little bit of an offset here because there's a bit of a phase change between the coils and the line. But the big takeaway here is that this coil is going to get, instead of 100 volts that each source delivers, it's phase to phase. So it's 173 volts. And that divided by the 10 ohms, that means that the current flowing through the coil directly will go to a maximum of 17.3 amps. Okay, and so then you take that and you multiply by each, and the square root of 3, and you end up with, well, how much does each of these sources deliver? If you watch it for a second, the kW right there approaches 3, and you won't actually see it get to 3, but it approaches 3, and so each one of these delivers 3 kW. Okay, so now let's go ahead and switch. Well, and by the way, that's a total of 9 kW across all of these. Okay, so now let's go ahead and switch this to the Y and see how it reacts with the same resistance coils. Okay, and so when we look at this, you can see that the total power that's consumed by this will climb all the way up to about 1 kW. I'm going to click on this one first, and there it is. And then this one goes up to almost 1 kW. You can see it on the bottom right is where I'm looking. And then right there, almost 1 kW. So they just, I'm just going, it's 3 phase, so they cycle through. And so that's what each one of these coils is consuming. Are the loads consuming the same? Well, if you look at the power, it's going to slowly go up until almost 1 kW. And then right at 1 kW. And then right at 1 kW. So that's the same, right? And over here, what's going on with these? Well, each one of these coils will get our phase to neutral voltage, okay, which is not the square root of 3 times higher. It's just 100 volts divided by 10 ohms, and that makes it 10 amps per phase, per line, right? So if you look, the Y will have the same line current as its phase current, okay? The current going through the coil is the phase current. The current going through the line is the same current, so they're the same, okay? However, if we look at our delta, this is our phase current right here, and the phase current gets up to about 17.3, where our line current will get up to 30, okay? So the line currents on a delta are the square root of 3 times higher than the phase currents of a delta. All right. So another thing that you can pay attention to is that even though I apply 173 volts across this single 10 ohm coil, you have to realize that there's a parallel path going this direction for those currents to flow. And that's where the rest of it comes from. Okay? So that's why our line current ends up being the square root of 3 times higher. All right? So that's everything in this one. This example is all 3 coils have the same resistance as these 3 coils. So here on this example, we have a delta and a Y load where each one is consuming the same amount of power. And what you would notice is that the delta, the resistances of these coils are 3 times higher than the resistances of the Y. And so how much power is consumed by our delta? Well, let's look at our loads, our sources. Our sources show us that it's going to climb up, and it climbs up to about 1 kW on this one, and this one is also 1 kW, and then this one is also 1 kW. And we could also go to our coils and look at our coils individually. Let me see if I can catch one. All right. So this coil is going to go up to about 1 kW right there, and then this one should be climbing up, and then this one is climbing up. So it makes perfect sense. So we're providing about 3 kW out, and we're consuming 3 kW on the load. So let's switch it over to our Y and look at that one as well. As you look at the Y, we have, well, we're going to have to sit here and wait for a second for it to build up. It's building up, and it gets up to about 1 kW, and then this one's going to climb up, and then this one's going to climb up. And you can see that the Y is still consuming the same amount of power as the delta. And another thing you can pay attention to is that the line currents on this, we're not changing our source voltages. So if our line currents are the same as the other setup, then line currents times voltages will end up getting you your power. So our line currents should be the exact same, which they go up to 10 amps on this one. And then if we go to our delta, what do our line currents end up being on this one? Well, they go up to about 10 amps on this one as well. Okay. Whereas on our delta, our phase currents are the square root of 3 times smaller. Okay, and we showed that in the last example, but you can still see it here as well. Okay, so that concludes this example, and then the next one we're going to go on to where all our phase current of our delta is equal to the line currents, or also the phase current of our Y, because our Y, the phase current and the line current are the same magnitude. All right, so. Okay, so here what we're looking at is the exact same voltage sources, and they're all 3 at 100 volts. It's a 3-phase source, and the way this one is constructed is you can see that these delta coils are square root of 3 times larger than our Y coils, and so we end up consuming a little bit more power on the delta side. We actually get up to, this is going to be, the delta is consuming the square root of 3 times higher power than the Y is, okay? But what you end up seeing on this example is that our delta line currents are, of course, square root of 3 times higher than the delta phase currents, okay? And if you look, the phase currents right here are about to get up to 10 amps, and then they go up to 17.3 on the line. Okay, so that makes perfect sense. But what we have in this situation is if we switch it over to the Y, we also have the same phase currents on our Y. Okay, and that's it gets up to 10 amps. So the difference here, though, is that the phase current and the line current on our Y are exactly the same, because there's no parallel connection like there is on a delta. Okay. So hopefully that illuminates the differences here. So thank you.